Let's see. All right. I think we're back from lunch, everyone. Welcome to the third session of the day. Léonard is going to start by telling us about the latest and greatest in an R4RS compliant REPL in 7K.
Hi. Thanks for having me. My name is Léonard Ernst O'Leary, and I'm going to present an R4RS compliant REPL in 7 kilobyte. You may have noticed that in the title it's 8 kilobytes, but it already shrank a little bit. So, yeah. This work has been made possible because of Mathis, who is right now in the room, and Marc, who is probably watching right now. So, hi Marc. So yeah, let's jump right into it. So, sorry. Okay. What is R4RS? So I'll start slowly because maybe some people don't know what R4RS is. R4RS is the 5th scheme standard, and it's what we consider as the first modern scheme. It was released in 1991, and so it's been a while. And just to refresh a little bit your memory, here is everything what is contained in it. So it has 164 essential procedures, 18 essential syntaxes, has file I/O, it has rest parameters, quasi-quote, unquote splicing, call CC, load, eval. So it has a lot of features. It doesn't have essential macros right now in the eval feature, but still it's a big it's a big standard, but big relatively to Scheme. And now let's just do a little experiment. How small is 7 kilobytes? So we are used to manipulate like gigabytes right now, so it's good to remember that what 7 kilobytes is. And if we take the first 2 pages of our paper as text, this is 7 kilobytes. So our goal today is to fit the whole R4RS standard inside 2 pages of our paper. So we'll talk a little bit about the technologies we used for doing this. So this talk is going to be split into 2 main parts. First one is going to talk about what Ribbit is. Ribbit is the system that we use to compress the REPL. So in short version, it's a scheme implementation based on a virtual machine that is compact, extensible, and portable. The second part of the talk is going to be how we changed Ribbit so that it can fit a REPL in 7 kilobytes. So a little bit about the origins of Ribbit. Ribbit was motivated by a fascinating project called Sector Lisp, which was able to fit a Lisp implementation with GC in 512 bytes. While a nice experiment, it's more a curiosity than an actual practical because it's not extensible or portable. So we wanted to take a different approach to reducing code like this, and this is what we present as Ribbit. So Ribbit is portable. We define portability as the effort required by a programmer to get the VM working in a different environment. Okay, and our approach is a bit different. So we implement by hand new virtual machines. And because the virtual machine is quite small, this takes about 2 to 3 days to do. So adding a new host is 2 or 3 days of work about that. And here are some implementation that we already have in Ribbit. So there's one in JavaScript, in assembly, in C, and there's more of them here below. As you can see, they all have a similar structure. We all have the RVM code, which is kind of a bytecode. It's not really a bytecode. I'll go more over on exactly what it is. And here we just have a while loop to represent the interpretation of this kind of bytecode. So as we can see, we have a couple hosts right there. Ribbit is extensible. So we added a new construct that we call define primitive that lets the user in Scheme write directly new primitives inside its Scheme code. So as we can see here, if we want to define the square primitive that will just square a number, you can use define primitive here to define it in Python and in C. And this can serve as a simple FFI. Note also that you could use define primitive to call, for example, libraries in Python or things like that to interface with them. Ribbit is compact. You may know about our previous work that was able to fit VM compiler and REPL in 4K. This, while impressive, it's a bit far from R4RS. It didn't support file I/O. It was a subset of R4RS, and it was 4K in the JavaScript host with the min library, which has less features. To compare it with what we have right now, this is what was in the previous REPL, and this is what we have now in the new REPL. So we see that there's a lot more procedures supported. And the whole R4RS standard is supported in the new version. Now I'll go a little bit about things that Ribbit do to compress the code. So one thing Ribbit do to compress the code is a liveness analysis. So it does a liveness analysis inside the source code by, for example, removing the read procedure if we only display. But it also does it inside the RVM. So if we never use a primitive, that, for example, put car here to print, it should be get car. So if you, if we never use a primitive, it is removed from the RVM. So this allows us to really tailor the RVM to what we really want. The RVM is the Ribbit Virtual Machine. So yeah, let's have a little bit of a closer look on how exactly Ribbit works. So we start with our program that we want to compile, and we start with an RVM implementation here. So we could choose any implementation that we have. There's a lot to choose from. Here we chose the JavaScript one just as an example. And we feed both of them inside the Ribbit AOT compiler. So the scheme is going to be parsed, expanded. There's going to be liveness analysis. And at the end, we are going to generate what we call the RVM code graph. So it's a graph that contains the values as well as the whole code. I'll go more over what is contained inside this graph. And then we serialize this graph into the Ribbit intermediate representation that we call the ribbon. So the ribbon is then going to be embedded inside our program. Our program. So our program is going to be embedding the intermediate representation. I told you earlier that it isn't really a bytecode, and the reason is because while doing this, we generate the whole RVM and we tailor it, we change it. So the compiler is going to maybe remove primitives or reorder them or remove features inside the RVM. So the bytecode here, you cannot take it and put it in another RVM. It's not going to work. You have to pass through the compiler for it to work. But this gives the compiler more power over what is included inside the final executable. Now we'll do a little overview of the code graph that we saw earlier. So in Ribbit, everything are ribs. Ribs are a three-field vector that can contain either instructions or values. Here on the left, you have a few examples of values that are contained with ribs. So the pair, for example, is a three-field vector where the first field is the car, the second field is the coder, and the third one is a tag to say that it's a pair. And ribs can be nested, so inside ribs you can reference other ribs or numbers. And the whole program is represented this way. For the stack machine, it's a pretty standard stack machine with 5 instructions that pretty much resemble the 5 instructions in Scheme. And we also have a small set of 18 primitive procedures that are used either inside the standard library or used by the compiler. I didn't include the I/O primitives because we changed them with the R4RS library, and we used our define primitive to do so. But if you want to do file I/O, there's a little bit of primitive to add, but it's not that much. Now we'll go over a little execution example. I won't say exactly how the program executes here. The only thing I want you to remember is everything is ribs in Ribbit. So you see here the program, the instructions get, const, call that you see in red here. These are instructions in Ribbit, and these are nested ribs. Yeah, so they represent the whole program. We also see that our stack is represented as ribs. Here, yeah, I didn't say it, but this is the exponential function here that has been compiled to the RVM code graph. So everything are ribs here. And the symbols as well are, for example, ribs that point to other information. Now let's look how a typical RVM looks like. So here we have the RVM in Python. So first we have here a section that embeds the ribbon. So here's the section where we input the ribbon. We have also here a section that decodes the ribbon. So it's going to transform this ribbon into the code graph. We have here a section that interprets the code graph. So it's running on the ribs and doing the different operations. And finally, here we have a table of primitive that is going to be used by the RVM code graph executor or the runtime to know which primitive is being called. So now we're going to go over a little bit about how do we serialize the program into the ribbon. Yeah. So first of all, the ribbon is made out of 2 main parts. There is first the symbol table and the decoding instructions. The symbol table is constructed from left to right. This is because it's simpler to decode it this way. In Scheme, often we start with nil and then construct our list this way. Symbols here are in reverse. So for example, if you look at the first one, it reads Izolk or something like that. If you reverse it, it's close. So it's for creating a closure. And we have, also, the symbol table is going to be represented as ribs in Ribbit. So here we have a link list. So the first one, we have the list of symbol with the tag that start with 0. And on each of them, we have, it links to a symbol in the symbol table. So for example, the first one is the rib, and we have a few anonymous symbols or unturned symbols that we just need to call. So there is, here is the representation of the symbol as ribs. Yeah, so, and the values of the global variables are stored directly inside the symbols. Now we're going to go over the decoding instructions. So to do the decoding of the ribbon, we use another stack machine that has its own instructions. So these are pretty classic instructions. We have push, that just pushes a new value on the stack. We have link, that takes the top of stack and links it, so by the third field of a rib. And we have merge instructions that take the two value on top of stack and create one rib with them. For example, the merge instruction is used to create ifs, because both flows are going to be on the stack, and we're going to take them to put them inside the if. Here I have a little animation about how this is all going on under the hood. We have the stack here. On the right, we have ranges that are associated with each instructions. So for example, the instruction push 0 here has a range 0 to 19. And when we are decoding, we take each of these instructions and running it. So for example, the first one is a push instruction. So we add a new rib onto the stack. And this rib links to a value on the symbol table. And while doing this process, so for example, here we have another instruction that creates another rib. And here we have another instruction, again, linking the rib. And note here that the instruction is what we call long. Some instructions can be encoded on multiple bytes. This lets this is because sometimes we need to encode the argument on more values. So at the end, we are going to end up with one rib containing the whole program, like that. And then the second phase is going to kick in, and we're going to execute this code. So now we've understood what Ribbit is. Now we're going to see how we enhanced it to fit a REPL inside 7 kilobytes. So the journey to 7 kilobytes. Here is a picture of the board in our lab that we had. And at first, as you can see, we wanted to call the paper R4RS because we didn't achieve the 4K, but we still achieved 7K, which is pretty good. And so we used a lot of techniques to shrink it down. For the rest of the presentation, I'm going to use a scale here to show you to show you how much kilobytes we saved by each technique. So as you can see by the photo here, we started at 18K. So the first thing we did is writing R4RS with style. So we rewrote a little bit the library because our first way of writing it was not optimal for space. So for example, using higher order functions or not boxing characters when dealing with I/O. So these are simple techniques of transforming the code a little bit. We didn't do too much of it, just a little bit. The second part that we did is we enhanced the encoding. So the encoding that I showed you had some flaws. For example, it was only using 92 codes. So the string that you saw is the ribbon. Is the ribbon it's the ribbon, and we can use 256 codes when we compile. Well, when we use compiled hosts. For example, on C and an assembly. This is because it doesn't take more space to represent this data inside those compiled hosts. So using the whole code really improved the compressing rate. The other thing is the decoding instruction that I showed you cannot represent a directed acyclic graph. It can only represent a tree. So this has some issues, and we'll go more over and how we fixed it. And the encoding is not specialized to the source code. So we have now a new encoding that can be specialized to the source code. So now I'm going to talk about the share instruction. This is the instruction that allows us to represent the code graph as a directed acyclic graph. As we can see here, we added a new instruction. So before the share instructions, we couldn't express a tree-like structure. We could only express a tree-like structure like this. This is a simple positive function that turns a number into a positive value. And we can see that the continuation of the if here, it has to travel two different paths. Either it is true and we do the multiplication, or it is false and we do the multiplication. So if we cannot represent a DAG, we have to encode the graph with the two flows that you see here beneath. With the share instruction, we can take a certain value on the stack and push it again. So we can represent the graph as a DAG as shown here. The second thing we did to improve the encoding is encoding specialization. Inside the all RVM hosts, we have special annotations that you can see here. These annotations, I won't go over what they do, but they give additional information to the compiler to do some modification of the RVM. Remember that we generate a whole RVM, so we can modify it while we compile to the final host. And here, this means that the compiler can have an algorithm to decide the best ranges to assign each encoding instructions. And here is the output of the compiler. And you can see that it assigned a certain range to each instructions. And because of the annotation that we have here, we are able to replace it after compilation to have this vector embedded this way. This lets us really fine-tune the RVM to the source program to minimize it as much as possible. And the algorithm inside the RVM, what it really tries to do is to minimize the use of long instructions. It will give better ranges to instructions that are used a lot with small indices. This way, it can really encode the fewer long instructions and compress the code as much as possible. The third technique we used is compression. So we used a classic algorithm called LZSS, and it's a compression algorithm based on back pointers. So instead of representing similar strings by just repeating them, we represent them as back pointers. So a certain offset back and a certain length. Our main challenge was to encode back pointer. Was the way we encode back pointers. So here is the way we did it. We reserved a certain range of the 256 code for compression, and on this range we took the second byte and combined it into one number. Then the compiler decides at compile time what would be the maximum length possible for a back pointer, and this information is injected inside the RVM. This way it lets us decode the back pointers, and by doing a simple division or modulo operation. So this is like the high overview of how we decode how we compress the code. And in a similar way, we embed the information like this inside the compiler. So now we can talk about results. We explained pretty much how the system works, and we were able to, a little animation here, I was really proud of it. We were able to define a REPL that is R4RS compliant inside 6.5K. Here it's written 666, but if you convert it into kilobytes, it's going to give you 6.5. As you can see, I just did a little example here where I did open an input file, actually an output file, and I write on it because the IO primitive was something that was a little bit tricky to implement. So I was kind of proud to just have an executable that's 6.5K and that can write to a file. It's pretty cool. And you may ask yourself, is it fast? Because we did a lot of things. So is it still decently fast? And it's still decent. We compared it to GSI, which is Gambit Scheme Interpreter. And as you can see, with all the optimization, which you can see more in the paper, for example, PNA is one technique we use to make it a little bit faster. We can see that it compares pretty well to GSI. If we add type checking, we see that it's a bit slower, but it's not that much. The only thing that is really slower is here the deriv benchmark, and this is because it uses a lot of higher order function with apply, for example. So we still have to look into that because why it's a bit slower, but we have a good idea of how to fix it. So future work. We believe that we can fit an R7RS REPL inside 15 or 30K. So we're gonna see if we're able to do this, but this is something we want to work on. So thank you very much for listening, and if you have any questions, I'll be happy.
So I'm sorry if I missed something very basic.
Yeah.
So you have this compiler that compiles your R4RS implementation into Ribbit. That compiler, is it written in Ribbit? Or?
No, it's written in Scheme.
Okay.
So we had some version that bootstrapped.
Mm-hmm.
So that means that it works with Ribbit. And there's no inherent difficulty of making it bootstrapping. Right now it's not bootstrapping, but it's just a question of making it work.
And the R4RS implementation itself, is that a straight up interpreter, or is it itself, or does it compile to ribbons itself, or how does that work?
This implementation is a library that we wrote in Scheme that is like.
But when you type in a scheme expression that it then evaluates, does it straight up interpret that expression, or does it itself compile it to a ribbon?
No, it doesn't compile. It's self-contained. It's an interpreter, so it works.
Okay.
Maybe
I can provide additional information. So basically, we have this library. We have R4RS as a library which you can include in your code. So basically, there are files which contain all the procedures and all that. For the REPL, we have a small interpreter written in Scheme, which is also in the REPL, which contains less feature than the actual compiler to make it small, have the smallest footprint while staying R4RS compliant in the REPL. So we have like a small interpreter written in Scheme, which can include, which is eval basically. And we also, for the rest of the procedures, they are written directly in Scheme, which can include them.
Yeah.
If that answers your question.
Hi, thank you. This was really cool. Also, just sort of a confirming question. So when I run the compiler, it produces this encoding decoding schema of the compiled Scheme code, as well as an implementation of a virtual machine in some language.
Exactly. Yeah.
Okay.
So
Yeah. So I guess two questions are: you mentioned it takes 2 to 3 days to set up.
To write a new RVM. Once it's written, you can compile to it pretty easily. Yeah, it's each RVM is about 200 to 800 lines of code, so it's really a small program to write.
I see. So it takes 2 to 3 days to generate that specific RVM for a given program, or?
No, for a human. So once you have an RVM implementation, you can compile instantly to other hosts. But to have a new host or a new language added to Ribbit, you can write a new RVM, and this takes about 2 to 3 days.
Right.
But it's a manual work. Like you code it.
Sure. Sorry, I was under the impression that you would generate an RVM specific to that program. Is that not true?
Yeah, we do generate an RVM specific to
maybe
that
I'm just
program.
confused. Yeah.
We do generate an RVM, but that is done by the compiler with annotations inside the RVM that you have written. So there's like 2 RVMs.
I see. Okay.
There's the one
So
as input with annotations.
Basing off of an existing one. Yeah.
And there's the final one. Yeah.
Got it. That's really, really cool. All right. Thank you.
So, if I wanted to make my own RVM, is there a standard by which I can refer to implement my own RVM in, say, RISC-V assembly?
There are a few implementation available on our GitHub that serves as like.
But you don't have like a formal spec of like when like this is the instruction and this is what it does, and Kind of like any other sort of ISA.
Yeah.
Do you have an ISA for this VM?
We don't have one yet. We are working on it to add more documentation for it. So there's a wiki ongoing. So if you go on it, it's quite small, but it's something we want to do so that people can implement their own RVM.
Yeah, I think that would really like sort of speed up the development of it. So if I wanted to spin one off,
Yeah.
I don't have to like kind of guess or know. I can look at the standard and then verify it myself that yes, this is indeed an official RVM, and then I can, then it's easy for me to compile to it, and then I can run that interpreter for that particular RVM.
Yeah.
Okay.
Yeah.
So first, just thank you for the talk. It was good.
Thank you so much.
Can we go back to the slide where you have your benchmarks?
Yeah.
So just a piece of advice here. Some of these benchmarks go back to Gabriel's original studies. Some of these benchmarks go back to Gabriel's original studies to write benchmark implementations. And so they're not that interesting anymore. For example, fib and ACK and TAC. Right? Well, those comes from the days when we weren't sure how to do recursion efficiently. So I would advise you to maybe look at some more modern applications.
We actually took the benchmark of Gambit. So these,
which is historically comes from Gabriel.
A subset of them, but it would be interesting to try to benchmark it on more benchmarks. Yeah.
And so my question now, have you ever, so these ribbons that you produce, right, are specialized depending on what is needed by the program?
Yeah, exactly, yeah.
Have you ever thought about doing that using a macro?
Using a macro inside the RVM, you mean?
Yes.
It's our annotation system is a bit like macros, but it's hard to have a system that works well because there's so many host languages. But yeah, it's we have like kind of annotation that can be embedded, and it's scheme code that runs in the background. So
okay.
Yeah. Thank you very much.
Any last questions? All right.
Hi, Audrey So, University of Washington. This is super cool and a very fun presentation. I'm just wondering, like, is there a reason why you want to get a very tiny interpreter? Or like a specific like use case, or is this just for fun?
I mean, doing it in 7K, it's a fun experiment, but there's actual use cases to this. For example, if we want to have a small JavaScript implementation that runs fast on the web, this could be like a motivation. Also for like embedding systems, or so there's a lot of use cases where having small implementation is useful. Actually doing it in like 4K instead of 7K, this is maybe more than a fun experiment than something. Yeah.
Okay, cool.
Thank you.
All right, I think this is going to be the last one, Alexei.
Hi, Alexei Rottle, Google. So I assume that your generated RVMs depend fairly heavily on facilities from the host language.
Heavily on what? Sorry.
Like you generate a CRVM, it runs on Ubuntu.
Yeah.
It can invoke arbitrary kernel functions from this like hundreds of megabytes of binary garbage. Have you looked into getting all the way down and stripping out the operating system so you can generate a tiny virtual machine image that just executes the program?
We haven't looked into this specifically. We have a x86 implementation, so this is quite like near the machine, but we still have the kernel to take care. So we could maybe try to go even lower. And
I mean, there could really.
OS.
I heard might be various other projects like this, but there could be an interesting direction because, like, one of the user-facing problems in Google Cloud is that it takes forever to spin up a VM because they have to ship a gigabyte-sized image to the VM hypervisor that's going to execute it on Node. If that image can become a 1,000 times smaller, that could be very interesting.
Okay, yeah. Thanks for that.
All right. I think we're going to take the rest of the questions offline. I have a surprise. Oh, let's thank the speaker one more time, please.
Thank you very much.
We have right now time for a surprise talk. Arthur had a quick major announcement.
Hi, so I'm Arthur Gleckler. I'm the editor of the Scheme Request for Implementation. I actually followed Mike Sperber, who used to be the editor. And I've been asked by the Scheme Steering Committee, which is essentially a group of... Oh, you still have your microphone on. You still have your microphone on.
Oh, sorry. Must be a bit awkward. Okay, here it is.
Yeah. Yeah. So I won't be that entertaining, but the Scheme Steering Committee is a group of folks who basically are the level above the working groups that are working on R7RS small and now R7RS large. They asked me to make an announcement because earlier today we got a new editor for the, new chair for the working group that's doing R7RS large. So let me just read this. This is actually written. So Mark, if you're watching, here I am. The Scheme Language Steering Committee, whose members are Will Klinger, Mark Feeley, Chris Hansen, Jonathan Rees, and Olin Shivers, these are all people who've been in the Scheme Standards effort for a very, very long time, would like to make the following announcement. Following the recent letter of resignation of John Cowan as chair of R7RS WG2, Working Group 2, we have accepted John Cowan's resignation with our deep thanks for his exceptional service. His leadership, devotion to the task, and many contributions have been extremely valuable for the evolution of Scheme. We look forward to the continued contribution of his expertise and input as the R7RS process continues. And then the steering committee has appointed Daphne Preston Kendall as the new chair of R7RS WG2. In moving forward, the steering committee intends to have more frequent interactions with WG2 with an overall goal of bringing the Scheme community together and finalizing the R7RS large standard in the not too distant future. Mark, and this is again from Mark Feeley, who's representing the Scheme Steering Committee. So that's the announcement, just a very quick thing. R7RS continues. So, I'm taking questions. So you ask, does Daphne bring new process to the new direction to it? She has definitely some new ideas. By the way, John Cowan strongly supported her and endorsed her choice, choosing her as the next chair. So she's written about that in her blog post about the whole process before she took over. And I'm sure new things she'll be writing more to come out. But yeah, they do have some ideas for simplifying. I don't want to speak for her. That's a good point. We should put something on scheme.org. Thank you for the point. As soon as I get anything, I'll put it up.
All right. Thank you, Arthur.
Yep. Thanks, everybody.